For a theory that's supposedly really complicated, quantum mechanics has surprisingly few rules. So these are the 4 rules that we're going to be learning in this course. And yes, if you pause and actually look at any one of these, it's going to look like complete gibberish right now. But you're actually going to meet these 3 rules in this video. And by the end of this video, hopefully we'll have a fairly good understanding of how they work. The last rule, the Schrödinger equation, is kind of the one that most traditional, Quantum 101 classes focus on, but I actually think it's kind of the least interesting, especially since these days, if you wanted to solve the Schrödinger equation, you would use some computational methods, and we will eventually go into that. Whereas I think more traditional classes spend a lot of time solving the Schrödinger equation by hand, which to me doesn't make sense. The other thing is, I think that these first 3 rules are usually taught quite abstractly, but I'd rather not do that. How about instead, we start off with an example that we can see with our own eyes, and we'll build up those first 3 rules. So this is what we're going to be using. It is a laser pointer and this Polaroid film. So this is the kind of film that your Polaroid sunglasses might be made of, but you can also just order it as sheets online. So that's what I've done. And this is like a cat toy. This is actually a quantum system, and one that you can see with your eyes. And I find it really, really helpful for thinking about these rules. So you'll see that this laser has a little filter on it. And that filter is exactly the same as this stuff. And the alignment is the same as well. So you can see here. And all it does is it makes sure that all of the light coming out of here is polarized. Now we'll get to what polarized means in a second, but first let's just play around with this a little bit. So firstly, what do you think will happen when I put this filter in like this, with the same alignment as that filter? Well, you might have guessed that it does pretty much nothing. And that makes sense, right? Because, we already have kind of made this light all filtered in that direction. And so, filtering it again doesn't do anything. So I'm going to just write that down. The light coming out of here is in this state. And I'm going to put this thing around it. In quantum mechanics, whenever we're talking about the state that some quantum system is in, we write that state inside of what's called a ket. And this is really useful. It's called Dirac notation, and we're going to use it again and again throughout the course. But don't worry too much about it right now. We're just writing down that in some sense, this light is in this sort of horizontal direction. Now, you may have seen this before, but what do you think happens when I put the filter in the opposite direction? So this way. Let's find out. And you can see that it pretty much cuts out all of the light. Not exactly, and that's just because these filters are not perfect, but if they were, this would be 100% of the light blocked. So it does seem fair to say that the light is in this horizontal direction, and vertical light must be the opposite, which is why this filter completely filters out the horizontal light. But horizontal and vertical aren't the only options for how we place this filter. So let's try rotating it. Okay, so we'll start with all of the light blocked, and then we'll slowly rotate. And you can see that more and more light is getting through, until eventually we're back to full brightness. So that's a kind of interesting result, right? So what do you think would happen if I put this at exactly 45 degrees, which is like halfway between horizontal and vertical? Well, let's see. That looks roughly right. So that's supposed to be a 50% drop in brightness. And I mean, depends on me getting the angle right, but yeah, that's plausibly 50%. So far, this all makes sense. But here is the mystery that we're going to try and solve for the rest of the video. So if we have this 45-degree light, we've filtered out about half of the light. So originally, all the light was pointing horizontally, and now we've filtered a bit more of it, and now we're going to put this vertical filter in again. So what do you think should happen? Well, the answer should be clear, right? Because I started off with all horizontal light, and yes, by putting this in, I filter some of that light, but we know that all horizontal light is the opposite of vertical, which is why this cuts out all of the light. And so putting this extra filter in shouldn't do anything. But have a look. Isn't that cool? It makes it get brighter. How is it that a filter can do this? Well, to understand it, we're going to need to learn some quantum mechanics. We've already started talking about the state that this light is in, but now we're going to represent that state in a slightly different way. So we're going to use little arrows to represent quantum states like this one. Those little arrows are called vectors, and the first rule of quantum mechanics is that every state can be represented as a vector. So let us say that this is the little arrow that represents this state. Now, yes, this is an abstraction. Of course, the light isn't actually a little arrow in any sense, but it's just a mathematical way to represent this same light. Now, when we were talking about these measurements, we realized that if this filter is aligned with this state, then nothing happens. On the other hand, if the filter is 90 degrees from this state, then that means that when you measure, the entire thing gets cut out. So we'll represent this measurement direction as an arrow as well. And it's pointing upwards. And it has the same length as the other arrow. Now let's look at the second rule of quantum mechanics. To figure out the probability that this light is going to be measured in this state, what we have to do is look at how perpendicular they are. And you can see that here, they're very perpendicular. So that means that the probability that this state is measured as being up is 0. Now let's instead rotate this measurement angle to 45 degrees. So if we do this, now that is represented by this vector. How orthogonal are these two things to each other? Orthogonal, by the way, just means like how much of a right angle is there between these two things. It's not like a complete right angle, of course. It's kind of halfway, because if it was like this, it would be a right angle. But if it was like this, they'd be perfectly aligned with each other. And so this is kind of halfway. So as you can guess, the probability that this is measured at 45 degrees is half. And just to make sure that everything we're saying makes sense, let's just figure out what should be the probability of measuring this state in this basis. Well, it should be 1, right? And that would make sense, because if this was rotated to here, how much would this vector be overlapping with that? Well, they're completely overlapping, so the probability of finding this state in the horizontal direction is 1. So our rule kind of makes sense. Now though, we're very close to being able to sort out that mystery from earlier. We have one more rule of quantum mechanics that I'm going to teach you, and it says this. Whenever you measure a quantum system, you actually change the state of that system. So it's not like in regular physics where, if I look at how fast a car is moving, that doesn't actually change anything about how fast that car is moving. In quantum mechanics, it does. So in our case, what that means is that if I originally started off in this state, but I measured it, then the thing that comes out the other end is no longer in the same state as the original light. The act of measurement changed it. And what has it changed it to? Well, if I do this measurement, then this means that the light that's come out has to be at the 45-degree polarization. In other words, originally this light may have started off in the horizontal direction, but after I filtered it, the rest of this light is in a different state, and that state is this. This is light that's been polarized at 45 degrees. So what the third rule of quantum mechanics, the measurement collapse rule, says is that if you measure the light in a certain direction, so in our case this was this direction, then the resulting light, so the light that did actually get through, now is in that state as well. And so that is what I've represented here. So in other words, it's the same thing to do this as it is to just take this and rotate it by 45 degrees. Although, of course, this one is going to be, 2 times brighter, just because this one filtered half of the light, right? Only half of the light actually made it through. That's an important subtlety, of course, because remember, only 50% of this light actually got through. But the light that did actually get through is aligned in this direction, and so we can call it 45-degree light. Now I think it should be a little bit clearer why we got that weird result earlier. So imagine if I had in fact started this light off at 45 degrees to begin with, and then I filtered it like this. You would only expect 50% of that light to drop, and here's why. The state of the light is 45 degrees, and the measurement is vertical. How much do these two vectors overlap? So the probability that this 45-degree light is measured as being up is half. And that's why half of the light goes through. And then it's no wonder that we got our original result. Because originally, yes, the light was polarized in the horizontal direction, but after doing this measurement, because of the measurement collapse rule, the new light is actually in this 45-degree direction. And so it makes total sense that half of that light gets through this vertical measurement. Still, it's very surprising to see this, right? And that's because we need to stop thinking of these things as filters. That's a very classical way to think about these measurements. But quantum states and quantum measurements really are different. And the measurement collapse rule in particular makes quantum mechanics quite different from classical mechanics. But this is a really subtle point, and I don't expect that at this point, with such a simple example, that you're convinced of it. So we're going to look at many more examples in the future episodes. But for now, let's just look at this example and the mathematics of it a little bit more closely. Because what I find amazing about this is that this very, very simple system actually has all of the mathematics of quantum mechanics in it. So by the end of this video, you will have met all of that mathematics for the first time. Now, again, I don't expect that by the end of the video, you will have fully grasped it and be completely comfortable with it, but you will have at least seen everything there is to learn about quantum mechanics, at least once. All right, so we've already talked about light that's in the horizontal direction, but of course there is an equivalent type of light which is in the vertical direction. And so I've represented that by this vector here. But of course, there's light in every possible direction, right? I can turn this around in every way. And so we want to be able to represent all of those types of light. So of course, any one of those can be represented by an arrow as well. So for example, if I have 45-degree light, I can represent it like this. And I've just made sure that these vectors are about the same length. So they're supposed to be length 1. That's kind of important. In quantum mechanics, we said that all quantum states are vectors, but in particular, they're vectors of length 1. And the reason for insisting that they all have length 1 is because of probabilities. You'll see in a second, but we want all of our probabilities to add up to 1. There's nothing actually special about horizontal and vertical light, right? Like there's nothing particularly special about those directions. But if you pick any two directions like this, so they're orthogonal to each other, then they define what's called a measurement basis. Okay, why is it called a measurement basis? It's because it's about measurements. And in fact, we know that this is a really simple case because we know that this vector and this vector were originally length 1, and we're going to shrink both of them by the same amount because 45-degree light is equally both of these. So whatever this is, they're the same length. So using Pythagoras' theorem, then you'll find that this should be the length, because if you have 1 squared, the hypotenuse squared, that is equal to 1 on square root 2 squared plus 1 on square root 2 squared, because that's half plus half. Okay? And so I'm going to put that 1 on square root 2 here, 1 on square root 2 here as well. This little Pythagoras' theorem calculation is actually really interesting because you see this half and half. Those were the probabilities, right? We wanted a probability of half, that if you have this vector and you measure it in the direction of horizontal or vertical, then you would get a probability of half that it goes through. So this kind of looks suggestive. And in fact, that is going to be the rule. The probability of measuring this state as horizontal is equal to this coefficient squared, and the probability of finding it horizontal is equal to this coefficient squared. So what we've just done is that we've said that light that's oriented like this is a combination of light that's like this and like this. So in other words, we've just said that this kind of light is a superposition of this and this. That turns out to be a very profound insight in quantum mechanics, that any light can be written as a superposition of other types of light. So if we take any measurement basis, like this horizontal and vertical light, then we can write any other type of light, however it's oriented, as some combination of this plus this. So let's just try and do it for a couple more cases. What about, instead of the light being oriented like this, so this 45 degrees, what if it's oriented like this? Well, let's just draw it again. We want to write this light as a combination of these two. So again, it seems pretty reasonable to guess that the length of these two is going to be 1 on square root 2. And the reason for this is that we know it should be equally this and this, because when we put in our filter, whether we put it in like this or like this, it cuts out about the same amount of light, which is 50%. So that suggests that these two coefficients should be the same size. But obviously this can't be the right answer, because we just said that this state is actually equal to this vector. So we want to take this vector and we want to like turn it over a little bit. Or another way to think about it is the way that we made this vector is by adding a bit of this and this. And if instead we want to make this one, instead we have to go from the origin the other direction. So we need the same components, but like that instead. Okay, so that means that we want to keep this vertical bit the same as before, because like before, we just want to go upwards. So that part is all exactly right, but it's this part that needs to change. Instead of going in the positive direction, we actually ended up going in the negative. And so another way to think of that is that it's like we multiplied the original vector by a negative number. So this vector times -1 is there instead. And so when you add this, which is this, and then you add that, you end up at the vector that you wanted. And so this is how we represent this state. But what about the probabilities? We still want the probabilities to be half. Is that going to work out? Well, we take this coefficient and we need to square it. Well, what happens when we square that? When you square a negative number, it becomes positive. And so even though this coefficient was negative, when we squared it, the probability is still a half. That makes sense. That kind of shows you why the squaring is important. You need to turn the negative numbers into positive numbers. But actually, this can go a little bit deeper. So it's possible to have states where these coefficients are actually complex numbers. And so then when you want to get the probability, you don't just square them, you take what's called the modulus square. Now, I don't think I'll cover complex numbers right now. I might cover them in a future video. But I think that this case with the negative numbers in the coefficients basically covers the interesting cases. So I'm not 100% sure whether I'll do the complex number thing. Maybe as an optional video, we'll see. Okay, let's do one more case where I turn this so that it's almost entirely pointing in the vertical direction, but has a little bit of horizontal in there as well. For this vector, we can see that there's only a little component in the horizontal direction and it's negative, and then there's quite a big vertical component. So there's going to be a smallish negative number here and a quite big positive number here. And then when you square it, you end up with probabilities that reflect this. Here we expect the probability of the horizontal component to be quite low, whereas we expect the probability of the vertical to be high. So let's check that. So we've got horizontal here, and you can see that cuts out quite a lot of it, so that probability is indeed small. On the other hand, let's do this one. You can see that that barely cuts out any, so that aligns with this being quite a big probability. For example, maybe this was -1 on square root 4, and this was square root of 3 on square root of 4. So when we square those coefficients, we end up with 1/4 and 3/4. Now I think you know how to take any vector pointing in any direction and then figure out what will happen when you measure it in the horizontal and vertical basis. But of course, that's not the only kind of measurement that you can do. Let's say that we actually started off with this state, so that is the horizontal state, and then we choose to measure it not in a horizontal or vertical direction, but at some angle like this. Now what's the probability that this light will go through? Well, again, we're going to write our state as a superposition. So this is what our state looks like. At the moment, we're kind of used to thinking of this state as not being in a superposition. I mean, it's 100% in the horizontal direction and not at all in the vertical direction, so it's like pure. But actually, that's just because we're thinking about it in the wrong measurement basis. The measurement basis that's relevant now is not the horizontal and vertical measurement basis, but the 45-degree angle and the 135-degree angle ones. They're 90 degrees away from each other. So that's this direction and 135. These two directions are orthogonal to each other, so they define a measurement basis. In fact, any two directions that are at right angles to each other form a basis. So it can be in any direction whatsoever. And they are opposite to each other, meaning that if you do one and then the other, it completely cuts out all of the light. So this is true for our 45-degree angle one as well. So if we do this and then the other one, you can see it completely cuts out the light. So these two are like the options. All light is a combination of being in this direction and that direction. But what about our horizontal light? That horizontal light is some sort of combination of both of these types of light. But exactly what are the coefficients going to be? Well, we can guess, like before, that the length is going to be 1 on square root 2, because they're both equal to each other. The probability, right, has to be half. But there is going to be a negative sign in here somewhere. Well, if I take this vector and I take the negative of it, then I end up flipping the vector, so it's here. And now you can see if I take this negative vector and this positive one, we get something in the right kind of direction, because it's like these two vectors are pulling in this direction, right? And so if you added them, you would get something like that. you can see that's the right direction by thinking of it like this. This vector pulls downwards and to the right, whereas this vector pulls upwards and to the right as well. And so when you add them together, the bit that pulled downwards and upwards, those two cancel out. But the bits that are adding to the right, those reinforce. And so that's why you have to add the negative version of this vector and the positive version of this vector to get this one. I want to show you this example because this idea of changing the basis that you're looking at a vector in is really important in quantum mechanics. When you are looking at this vector just in terms of this measurement, it seemed like, oh, well, this is like a pure state, you know, it's going to 100% go through this, this measurement and get cancelled out by this one. But on the other hand, when you think about any other measurement, so rotating this by any amount, this vector is now actually a combination of two other vectors. So in general, whatever type of measurement you're trying to do, what you have to first do is you have to write the vector that represents the state of this light in terms of these two basis vectors, and then look at the coefficients and take the square of those to find the probability. And that is the probability that this light, when you do one of these two measurements, will get through that measurement. I just want to do one very last little bit of maths to solidify some intuition that you may have already built up. And that is that there's a slightly easier way of figuring out what the probabilities are going to be than just writing out this whole thing, like figuring out what this vector is equal to in terms of these two basis vectors, and then multiplying and then squaring the probability of these coefficients. The way you can do it instead is using something called a dot product. So say I'm interested in this probability. That's the probability that my state is measured in this direction. Well, instead of writing all of this, what I could do is draw the two relevant vectors. So that's this vector and that vector. And I want to draw them both as having length 1. And then I take the dot product between those two vectors. Now, the dot product is a way of measuring how perpendicular or not perpendicular two vectors are. And if this sounds familiar, it's because we've basically been doing it all this time. The simple way to take the dot product between two vectors is to look at the angle between them, and then take cos of that angle. Now this makes sense because if the angle was 0, in other words, the two vectors were overlapping completely, then cos of 0 is equal to 1, so the dot product is very big. On the other hand, if they're perpendicular to each other, the angle between them will be 90 degrees, and then the dot product between them would be cos of 90, which is 0. So in other words, the dot product measures how aligned or not aligned two vectors are. And in this case, because the two vectors are not perfectly aligned, but they're also not perfectly orthogonal, we would expect something between 0 and 1, and that's the case. So cos of 45 degrees is equal to 1 on square root 2. That means the dot product between these two vectors is 1 on square root 2. If you'd rather not use this new language yet, that's totally fine. We will see this dot product again a few times. The way to write that in quantum mechanics is you take the dot product. So this is the crazy notation for the dot product in quantum mechanics. So there's one of the vectors, there's this one, and then you take the other vector and you would write it as normal, except for the bit where this bracket is flipped around. So this dot product, in this case, is equal to 1 on square root 2, but to make it into the probability, you've got to take the square as before. Okay, so that's all the mathematics that I wanted to show you in this video. Remember, this is the main mathematics for quantum mechanics. You've seen it all once, though I don't expect that you fully grasped it, because if this is the first time that you've seen vectors, then this was a lot to take in. And I think that the best way to learn quantum mechanics, like any physics subject or maths, is to do a lot of problems. And so I recommend going back through this video if you really want to learn it and trying out all these problems on your own. But if that's not enough for you and you'd like a little bit more help, I was thinking about actually running this as a live course. So the lectures would be these videos. They'll be free on YouTube for everyone. But if you do feel like you want a little bit more, then I was thinking about doing sort of tutorial style sessions where we go through homework problems and try and understand this in a little bit more depth. So if that's something you're interested in, there'll be a link with some information about that in the description. Either way though, there's one last thing that I want to talk to you about in this example, and that is the meaning of this superposition. So this equation says that this type of light really is both this type of light plus this type of light at the same time. Now, what does this actually mean? We'll address this a lot more throughout this series because it is a very important question, but I at least want to address one common misconception. At least for me, it was really tempting to think that there are little particles coming out of this light, and those particles are called photons. And when you turn this light down a whole lot, eventually you only have a few photons coming out per second. Then it's kind of tempting to think that some of these will happen to be this type of light, and some of this will happen to be that type of light, so that when you do a measurement at 45 degrees, what you're doing is you're cutting out the ones that don't align with this measurement. So that would be these two. All right, so this is actually the wrong way to think about this. Actually, polarization of light is very much a wave phenomena, even in classical electromagnetism. I actually did another video where I kind of talked about this a bit, so I'm going to play a very short clip from that video. Light's whole thing is to harass charged particles like this electron. So this is what I mean. Imagine we've got some light coming along. I've represented it like this because as the light passes by this electron, these little things are supposed to represent the force that the electron will feel because of this light. So you can see that this light is first pushing this electron up and then down and then up and down. So as the light goes past, the electron will jiggle perpendicular to the direction of the light. But we live in 3D space, and so that leaves the light with lots of different options in terms of harassing this poor electron. So one option is that the light is oriented like this, which means that the electron will jiggle up and down as the light goes past. But we can orient the light anyway. So it could be like this, which means that the electron will be jiggling forwards and backwards. But it can be any other direction as well. So if I put the electron here and the light is coming towards, that's directed like this, we'll call that horizontally polarized light, whereas light that is oriented like this is called vertically polarized light, and you can have every option in between. So if the light was like this, we could write the state of the light like that. If I take two of these, and let's say this one is oriented horizontally and this one is oriented vertically, and I combine them, I can actually make any other type of light that I want. Here are two laser pointers, and this one only gives out horizontally polarized light. This one only gives out vertically polarized light. And my claim is that by combining these two lasers, you can actually get any other qubit that you want. But it just depends on how you combine them. So for example, which one is stronger, but also how in sync or out of sync these two lasers are. That's really not obvious, so I'll try and prove it. Say that the light that you really want is this kind of 45-degree light. So that's light that originally pushes in this direction and then eventually will push in that direction. How can I get that? By just combining the two bits of light that I do have, which are oriented like this and this. Well, here's what would happen if I just shone some horizontally polarized light at the same time as some vertically polarized light. At first, this one is pushing in this direction and this one is pushing upwards. So in total, it's like this electron's getting pushed up and to the right, which is exactly what we wanted this light to do. So you can see that shining these two things at the same time just gives you light in the 45-degree polarization. That's not going to be quite right, because if you just shone these two bits of light, then you're going to get something that's a bit too strong, even if it is in the right direction. So you kind of need to tone both of them down. And these two factors just represent how much you're going to tone down both of them. You got to do a little bit of trigonometry to figure out that those are the right numbers, but it's not a really big deal. The point is just combining horizontal and vertical light got you the light at 45 degrees, which is what you wanted. So as we saw in that video, the way to think about this 45-degree light is that it's a wave, and the wave is pushing in the 45-degree direction. In other words, an electron that ends up in the path of that light will be pushed that way. So that is the combination of two other waves of light, and those are pushing in the right direction and the up direction. And together, it's the same as if they were pushing at 45 degrees. So I think that it is correct to think about light as a wave, even in the quantum context. But what's different in quantum mechanics versus classical mechanics is what happens when you do a measurement. So we have this light here, and let's say that we make it much, much less bright. So we put a filter here, so not much light is coming out. What that will do is it'll make this wave a lot less wavy. Let's say that we made it so much less wavy that only a little bit of energy per a second is reaching this back wall. In fact, let's say that so little energy is reaching here that only 1 photon's worth of energy is getting to here. So a photon is the amount of energy that is like the minimum amount of energy that you can receive from light. You can either receive a whole photon or a multiple of photons worth, but you can't receive anything less than that. So what happens then when you put a filter here? Well, so far we've just been saying that there's a 50% chance that the light will go through because that's this coefficient squared. And all we meant by that is that 50% of the light would go through and 50% wouldn't. And in classical electromagnetism, that is what would happen. No matter how weak this light is, 50% of it will go through and 50% of it will be absorbed. But not in quantum mechanics, because there is this idea of a photon and you can't absorb less energy than a photon. So if there's only 1 photon's worth of energy going through per second, then there really is a probability that you'll get a whole photon worth on one side, or a probability that you will not get any photon. And so that is what that probability is. There's a 50% chance that you will detect 1 photon of light at this wall, and there's a 50% chance that you won't detect anything at all. So in that way, this system is a little bit different in classical mechanics versus quantum mechanics. So I think it's right to think of quantum systems like this as wave-like, but then when they're measured or they interact with another object, they have some particle-like properties in that interaction. Anyway, that was quite hand-wavy, but we'll come back to the question of what exactly is a superposition in quantum mechanics again and again. And I think in the next video, we're just going to do another example that's sort of similar to the light example in its mathematics, but is very different in context. So we're going to be talking about the spin of electrons. Meanwhile, let's recap what we went over in this lesson. First of all, we covered the superposition rule, which said that every state of a quantum system can be represented by a vector. And in this case, the vector was a 2-dimensional vector. So in other words, an arrow on a flat piece of paper. So whatever the state was, you could represent it something like this. And we also found that we could write this quantum state as a superposition of 2 other vectors in a particular basis. So to find out the probabilities from doing a particular measurement, you have to write the state in that basis, which we've already done, and then you look at these coefficients a and b, and you take the modulus squared of them. We also covered another rule for finding out these probabilities using the dot product. We looked at it very, very briefly though, so I won't cover it here because I think we will come back to it in a little bit more depth later on. All right, so that's the probabilities, and then one last rule, which is the measurement collapse rule. That rule says that after measuring this, so after the light does go through horizontal, the state is now horizontal. So in other words, the state went from being a superposition of both horizontal and vertical to just being horizontal. So well done you, you've now met 3 out of 4 of the rules of quantum mechanics. If you are interested in doing a few more problems to help you solidify what you've learned, then you might be interested in checking out the live course. Link is in the description. I'll also link to the rest of this video series when it's out.